Fantastic. Is everyone able to see my screen here?
Yes, we can see it.
Great. Awesome. Well, I wanted to first thank you guys for the time, for allowing Vectra to come in here and kind of present to you guys our model of zero trust and how we fit into the zero trust architecture. My name is Landen Brown. I'm your lead federal technology evangelist. Really, all that means is I love talking about Vectra and I love technology. But if you guys do have follow-ups that you guys would like to reach out on after the meeting, my contact is going to be listed on this first slide as well as the last slide. So what are some things I want to cover? First, I'd like to cover the overview of what is Vectra, why Vectra, what differences do we actually bring to the table, and how does Vectra play a role in our SOC? And not just a role, but a tangible role, something you can relate to and something an analyst can relate to. So let's start with what is Vectra. Vectra is the only true AI solution that does PCAP analytics. When we look across this space, what we mean by that is we're the only company focusing on surfacing threat activities and malicious behavior using machine learning, right? And so again, across the industry, what we see is a large focus on signatures, a large focus on surfacing data that is anomalous, and also using ML enhanced signatures. And what we're primarily focused on is building purpose-built machine learning models to address each one of these problems in the threat actor space. And so really, how do we put the AI in Vectra AI, and what does that mean for the analyst, right? If we can use AI effectively to reduce the load on analysts and allow them to rely on the detection efficacy of machine learning, then what that does is it replaces their time-intensive tasks. Traditionally, what analysts are doing today is spending the majority of their day focusing on detecting threats and doing investigation. If we can transfer that load to the response mechanisms and the response and SOAR automation functions that analysts usually take, then the actual value to the environment in terms of surfacing threats and being able to respond to them quickly and effectively goes up. And so in today's world, as we look across the threat actor space, specific to nation states, it's impossible for humans to cull through massive amounts of data that's being generated, whether this is AI curated malware being generated by nation states that is consistently hitting relay systems and penetrating into the environments of the intelligence community and the DoD systems and the FSI space. It's impossible to rely on humans to be able to cull through this massive amount of data when an AI algorithm is producing it faster than humans can think. And so the purpose of AI and the purpose of the AI that we use and how we are approaching AI is to replace that load, or I guess transfer that load to machine learning and allow the analysts to do what they do best, which is respond effectively to cyber threats. And so how does that differentiate us in the zero trust space? Really what we're focused on doing is the continuous assessment of trust, the enforcement of access, and presenting the context and correlation of detection events in the environment clearly and intuitively to the analyst. And so some key points about what is Vectra overall is we're true AI and ML. We understand that this is a buzzword in the industry, and this is something that has diluted the value of true AI and ML and the perception of that. So we encourage AI skepticism, and I hope you guys build your skepticism and understand Vectra a little bit more throughout this presentation. But we have over 50 patented neural networking machine learning models that we're using that are purpose-built to solve specific problems and challenges in the space. We're completely signatureless, we're completely agentless. From an architecture perspective, we usually sit on a span or a tap, maybe a packet broker like Gigamon or Ixia to ingest the PCAP data across the environment. And lastly, and most importantly, when we look at the federal environment, a lot of these environments are air-gapped and also rely on heavy encryption, especially the classified spaces. And so it's very important, and we're very proud to say that we don't require any decryption of the traffic. We're purely focused on using the TCP header information to fuel our threat detection models. So how do we make this a reality, right? This is all great on paper, but how do we actually do it from a technical perspective and a political perspective inside our company? So what we've found is that the most effective way to approach this problem is to start on the security research side of the house, which is our security researchers that are coming out of the intelligence community themselves, consistently doing the investigation and analysis of how new threats are using protocols across the environment, right? And once they have kind of built that portfolio portfolio of key indicators of how attackers are creating new methodologies within the environment using traditional protocols, we take that to the data science team. And the data science team looks at the problem set in whole, and they pick specific machine learning model approaches to address that problem and codify what we found from the security research side. So how do we build these AI detections? It's very important that we're focusing on solving the right problem the right way. And so how do we do that? We target the real world methods that attackers are using, right? And should be independent of tooling, right? Whether they're using Metasploit or tools off of a Kali box, the tooling that an attacker is using shouldn't matter. The independent of destination or environmental variables, right? These models should be able to learn in a perfect world what is unique to each environment, right? And so the next step would be getting the right data. In order to solve the right problem, you need the right data. And so it's important for us to say, as we're building these machine learning models and taking that valuable research from our security side, to say, what data do we need to gather for these models in order to actually produce efficacious alerts for the analyst? And so the last step here is choosing the right machine learning approach and the right algorithms for the right problems. When we look at command and control, lateral movement, persistence, all of the things that attackers have to do, there's different ways to approach each one of these from a machine learning model perspective, right? And what we see across the industry is that a lot of companies claiming to use AI are very focused on using general purpose algorithms, right? That do work. They provide some level of efficacy, as you can see here, but they're not great at solving or they're not good at solving things fantastically. They're just good at solving things. And so what we're focused on is using the right machine learning model approach, the specific algorithm that has the highest efficacy for that one problem. And if we can solve one problem well, that's what we focus on doing the most. And that's what brings us joy as a security company, being able to do one thing very, very well across the space. And so what does that look like from a technical perspective without going too deep, right? HTTPS tunneling is something very hard to detect, right? When you have computers beaconing out to advertisement servers or beaconing out to Facebook or people interacting with APIs across the environment, a lot of these things could look very similar to C2, right? And so the challenge is choosing the 0.1% of beacons that might be attacker behavior, right? And so how do we do this from a machine learning model perspective, right? This is the actual model that we do C2 detection based on HTTPS tunneling, where we're taking time series data from a sub-second data transfer pattern, and we're pushing that into a machine learning model to learn exactly what is not only anomalous within my environment, but is it indicative of how an attacker would conduct C2 as well? And so with that, we don't just have one model here and one model there. Each one of these behaviors as it relates to command and control, reconnaissance, lateral movement, exfiltration, et cetera, they all have an individual machine learning model and an individual methodology purpose built to solve those problems, right? When we look at something like RDP recon, or we look at stage loading, shell knocker, data smuggling, all of these things require a specific approach and a specific machine learning methodology. And we provide those in our portfolio today. And so how does Vectra take all of this, what we've built, what we aim to build in the future, and how do we actually play a tangible role in your SOC? I think a fantastic example of the value of zero trust and how AI can complement that could be highlighted in something like a supply chain compromise. And the most relevant supply chain compromise that we're all aware of today is Solarwinds. So I thought I would include this, right? Where the attributes of this breach are to say that we don't know how the attacker got in the environment. There's no method of entry. There's no footprints. There's no trace that they came from, laterally moved to set persistence within the environment. There's really no indicator that an attacker is there. And second, there's no signature that can detect that a legitimate tool, often whitelisted, is now conducting some kind of a malicious behavior. Right. And so using machine learning, we've been working closely with a few intelligence community partners to TCP replay some of this behavior, right? And from a zero trust perspective, this is very important, right? As we evaluate what is zero trust, it's never trust, always verify, even for your most legitimate resources, users, hosts, et cetera. The purpose of continuously analyzing, that person's trust is incredibly important. And as we see the legitimate tool Solarwinds start laterally moving through the environment, taking over the SAML signing certificate and compromising the actual SaaS application, we kind of see the value of how zero trust would have effectively solved this problem in the first place. And so how do we do this? The first things that we're focused on capturing are the PCAP data specifically, right? That allows us to capture the interactivity between hosts within the environment. Second, it's very important that we have the host information, but we need user information as well. And so we have specific machine learning models that are built to evaluate Azure Active Directory behavior, Office 365 user account behavior, AWS control plane information, Azure, GCP, Okta, et cetera, and combine all of these to perform that continuous assessment of trust across the enterprise and be able to track not only is a host compromised, but is a user compromised and then compromising hosts or resources throughout the environment. And so again, we're focused on doing one thing very, very well, which is threat detection based on machine learning in the NDR space. But it's very important to say, that we are focused on that one thing that leaves many other actions to be taken, especially from a zero trust perspective. Part of zero trust is being able to restrict resource access, lock a host down, disable a user account, et cetera. And those are things that we want to integrate directly with. And so what you see on the screen right now is exactly our current integrations list, from EDR to firewall, SIEM, SOAR solutions, Zscaler, things like identity management, et cetera. So if it's not out of the box already, which we have a massive portfolio of things that we do integrate with today, we do have a robust published API for people to kind of start creating those integrations themselves as well. And so with this, as we talk about Vectra and we kind of pivot over to the purpose of this call, which is the ATARC Zero Trust Lab, what are the benefits and pitfalls of zero trust, and how does Vectra contribute to the benefits of zero trust? Well, we performing that continuous assessment of trust, right? The never trust, always verify approach is very important to us, and something that we do natively with machine learning, right? Identifying and stopping malicious activity or privilege creep, restricting resource access to those that we trust. All of these things fit into the benefit that is provided by zero trust. And logically, from an engineering perspective and from a leadership perspective, this sounds fantastic, right? But I think it's very important to identify the challenges that we're facing in the industry that we have faced for the past decade as it relates to actually implementing a true zero trust architecture. And so what is often overlooked when pursuing zero trust? I think the first tendency is to choose a solution that fits but doesn't fit well, right? And what I mean by that is that a lot of solutions have a piece to play within zero trust, but not a lot of them cooperate or work together well. And so it's very important that, in a zero trust architecture, every single tool is relied upon to do a specific function, but also to feed the efficacy of that function to another tool so another tool can do its function. The second tendency is to choose a tool or choose one tool for too many facets of zero trust, meaning that you're choosing a single tool to perform many different actions in the zero trust space. And from a theoretical perspective, this is something we would all want. The problem is that there are many solutions that try to solve every single problem. And I think across the industry, what we're coming to find out, especially in the government space, is that it's very hard to do everything well, but it is much easier to do one thing very well. And the third tendency is to rely on anomalous data alone. As we look across the industry in the AI and ML space, what we see is a large focus on just surfacing anomalous behavior. And if we evaluate the federal environment, what we see is that everything is anomalous, right? We have administrators performing ad hoc tasks across the network. If your administrator is truly doing his job, he's going to be doing anomalous things to repair the network, fix the network, patch machines, et cetera. Users do anomalous things regularly, even if they don't have privileges. And so the reliance on anomalous data behavior or anomalous behavior alone has unintended consequences. And those consequences range from small things all the way to, in a zero trust architecture, your users being completely restricted access to all of the resources within the environment because they did something not malicious, but anomalous. And so ultimately this leads to, from a logical perspective, and as we think about zero trust, really an oversimplification of the topic and the actual ability to implement zero trust. And so what is, in our opinion, as a company, the most important factor in taking action with zero trust? You know, the most purpose-built thing zero trust is meant to do is ensure that only trusted devices and users are able to access resources in a very, very simple way. Or in a very, very simple explanation. But in order to take a efficacious action, you have to have an efficacious detection. You actually have to rely on the effectiveness of your NDR, EDR tools to produce an alert that is of high value to you. That way, we are not, I guess, experiencing the unintended consequences of artificially and incorrectly restricting access in different corners, right? And so the value of your detection truly impacts and directly relates to the value of your overall zero trust architecture. And so can AI and ML really make a difference in this space when it relates to zero trust? I think it's first very good to talk about what is AI and ML. I'm saying this a lot. I'm talking about machine learning models. And a lot of this could just be perceived as marketing. So I think it's important to say, what is AI and ML? I've kind of explained to you how AI and ML is being used to solve problems, but how is it being used to solve problems across the industry? And can the same AI and ML approaches be used universally here? And so this is kind of a graph from a institution depicting what is artificial intelligence and defining the terms. So artificial intelligence really is any technology that is able to approximate the rational output of the human mind. Now, this could be very simple. This could be, if you're a programmer in the crowd here, an if statement, right? If this, then do this. This is a rational output that is expected, or I guess what you would expect from a human to produce. Very simply, that is artificial intelligence. Now, the reason I mention that is because it's very easy, based on that institutional idea of data science, for any company to claim that they use AI. And so there's simple forms of AI, and obviously AI gets more in depth, but under artificial intelligence, inside of artificial intelligence, we have machine learning. And machine learning is specifically designed to make predictions based off of inputted data, which is where we sit a lot in the space. We do have different forms of machine learning and some deeper subsets here, but these are the two main topics in terms when we reference AI and ML, and this is kind of the ecosystem that they live in. And so when we speak about machine learning, right, specific to Vectra, we're using unsupervised and supervised models, right? And what this allows us to do from an unsupervised perspective is do learning local to the environment, right? So these models are based on unlabeled data, but they're taught and trained to learn the relationships between data in a local environment, meaning that you can install Vectra in any environment and it will learn specific to the environment and not flag on things that are, could be perceived as a signature. Second, we're using supervised models as well. And supervised models are taught or trained to label new events on labeled data, meaning we may understand what ransomware file activity looks like across the network, right? It's very indicative of attacker behavior, very obvious. And so we may be able to build a model that is built to perceive that data and then produce a result, an expected result from the prediction and I guess from the learning of an environment based on what we have taught it prior to introducing it to the environment. And so our portfolio exists of machine learning models that are both supervised and unsupervised. And each one of these models plays a particular role in threat detection. But all that being said, machine learning books are big, right? When we look at, if you were to take a crash course on machine learning, it would be sometimes 5 to 25 hours long. There are unbounded number of methods and approaches to take with machine learning. They're heavily customizable, and these approaches can also be stacked and nested between each other. And so it's very important to recognize that when a vendor comes and says, we use AI and ML and we contribute to X problem or X challenge, it's very important to understand, how does the vendor utilize AI and how do they utilize ML? And that the approach of how they're using AI and ML is more important than if they actually are. And so back to the no free lunch theorem, this theory that you can use a general purpose algorithm to solve everybody's problems is from an efficacious level very, very low, right? And so there's no silver bullet. There's no correct model to use for every challenge. There's no single algorithm that performs best from a computational perspective or from a threat identification perspective either. And so this no free lunch theorem means you have to use the right data for the right problem. And again, we're really focused on using the appropriate machine learning model approaches and choosing a highly specialized algorithm to solve specific problems like C2, lateral movement, persistence, etc. And so what difference does that make? It introduces a higher quality of alerts to the analyst, right? Less noise of just anomalous data alone, right? Attacker behaviors are not just weird behaviors, but they're indicative of how an attacker would do this. It provides you full coverage across the network, right? Cybercom said it best to us when they said that we're really good at providing coverage for the known bad, but Vectra is fantastic for providing coverage for the unknown bad. And that kind of covers that, or it plays to that full coverage perspective, right? And it's very important as well, this last piece of lightning speed, to be able to produce results from a machine learning model very, very quickly. And so our models are trained with that in mind as well. And so what I'd like to do now is kind of pivot over to our actual demo environments to show you, what does the product look like from an analyst perspective? How does it correlate data? How does it surface data, et cetera? And so there's two lab environments that I intend to use to showcase these things. The first is our corporate integrated ecosystem, which contains SIM solutions, SOAR solutions, EDR tools, firewall integrations, et cetera. Everything that you would need to showcase, I guess, the most effective, or I guess the most representative model you could get of zero trust. And secondly, we do have a built infrastructure within the ATARC lab environment. This is a fully developed and interactive environment. We actually lifted some of the labs that we have internally, and we're able to transfer them and bring them into the ATARC lab. And this is what that looks like. It's a very complex environment where we have, our attacker subnets, our user workspace here with the machines there, the server subnet, public management, sensor subnet, et cetera. And so all of these different environments are built to mimic what an on-prem or a cloud environment truly looks like. And so we thought it'd be very powerful to use this environment to talk through a scenario or two that you guys have provided us. And so with this, what I'd like to do is stop sharing my screen, and I'll go ahead and share out my window here for the demo. Are you guys able to see my new screen here?
Yep,
Yes.
you're good.
Fantastic. So what we're looking at here is the actual web interface of what we call the brain. And so we mentioned a little bit of architecture beforehand. We have what are called brains and sensors. And the brain is primarily just the physical, virtualized, or cloud-based appliance that does the actual analytics and computational analysis on PCAP data as it comes to it. And how does it come to it? Well, that's where the sensors come into play, where the sensors are sitting either on a span or a tap, or on a virtual port group, or maybe being fed by an Ixia or a Gigamon and forwarding that PCAP data to the brain for analysis. And so on the brain exists this web interface here that showcases what learning, what detections, and what context and correlation has the brain seen through its analysis of metadata. So if we dive into the host tab, we can kind of see an example of what criticality quadrants exist for the brain to populate into, as well as a summarized view of what some of these hosts are from a node perspective. And so there's two main scores for how the brain associates hosts into a criticality quadrant and makes the matrix for how these hosts traverse the criticality quadrants. And the first is the threat score. And we can see an example of this in the summarized view that we just saw a second ago. And we can see the threat scores associated with the different activities, right? Smash and grab being 60, hidden HBS tunneling being 70, right? Each one of these behaviors has a potential to cause damage within the environment. And that's what the threat score directly maps to, is what is the potential for damage within the environment. When we look at smash and grab, when we look at hidden HBS tunneling, file share enumeration, port sweeping, each one of these has a specific potential potential to cause damage, and they operate on a variability basis. As you would expect with machine learning, there are weights and graphs and all kinds of data input and predictions. And so it's important for the model to be able to operate on variability, meaning that, if we see RPC recon and suspicious remote execution on this host, the actual threat score may differ throughout the environment as the models see things like prior attacker behavior, lateral movement, successive attacker behavior, and additional context. And so the second score here is the certainty score. And very, very simply put, the certainty score relates to the machine learning model's ability to observe and detect behavior that is away from the baseline of normal. And this is anomalous behavior detection. Now, we do have models dedicated to this because even though relying on it alone is not efficacious, it still plays a critical role within the environment to determine what is attacker behavior. And so how do we use these two things together? Well, it's very important that we're not just flagging uncertainty and the ability to see anomalous data, and we're not just flagging on threat or an activity being conducted within the environment that could be benign, but instead we're flagging on both. So we couple the two data structures together to say, is this activity from a threat perspective, a threat score perspective, not only bad, right, and could cause damage, but is this activity indicative of how an attacker would conduct this activity? And second, are we certain that this is abnormal for my environment as well? If we can couple those two data structures together, then the actual efficacy that we're providing the analysts in terms of their ability to respond to events goes up drastically. And so with this, I'd kind of like to take you through a scenario that I mentioned earlier within the slides, which is the Solarwinds breach here. And again, I think this is not to pick on Solarwinds or to keep making this relevant, but I think in regards to zero trust, Solarwinds could have been mitigated had a effective zero trust architecture been in place prior, right? And so again, we don't know the method of entry here. We don't know that there is an attacker within the environment or that the compromised source code is running within the environment. All we know is that there is attacker behavior being surfaced within the environment, and I'd like to walk through that. And so this is an actual TCP replay of what we received from one of our customers that unfortunately we can't name within the federal space that allowed us to run this TCP replay through our models to identify this behavior or see if we could. And so this is the first thing that we saw. We see the command and control coming off the host to what we know from a post-analysis perspective is the randomized domain name here. Second, directly after receiving instructions from something like a command and control interaction, we see immediate LDAP queries and RPC recon, right? The attacker is trying to locate the domain admin account and locate the domain admin machine here. And, to no one's surprise, he successfully does this, right? And so what he does is he does this suspicious remote execution to what we know as the domain admin machine. And what he's doing here, again, what we can reference from post-analysis perspectives across the industry, is he's stealing the SAML signing certificate, which he uses to then compromise the domain admin account that oversees Azure Active Directory and Office 365. And I'd like to pause here because I think it's very important to recognize that if we had an analyst in place that was able to observe this behavior, if they were able to walk in the morning, set their cup of coffee down, log into their computer and see this activity, their response would probably be to either lock down this host, or if a zero trust architecture was in place and we started seeing this activity, an effective zero trust architecture would have stopped this behavior immediately. And so unfortunately, none of those things were in place. So we kind of get to pivot and see what did the attacker do when he did get access to the domain admin account. But if you were to have been able to take those countermeasures at this perspective or at this place right now, the Solarwinds breach would have been over and mitigated, right? Unfortunately, again, we didn't have that luxury. So let's pivot over to see what did the attacker do with the domain admin account once he did get access to it. So we're left off with this bookmark here that you may have seen on the last page that's saying ultimately an account is being logged into with high privilege using a service and from a host that has medium privilege that is abnormal for my environment. I've never seen this in my environment. And we're flagging for a threat of 95 and a certainty of 95. And the reason we are doing this, such a high threat and certainty for the first detection on an account, is because the models are already associating all of the prior attacker behavior that has been conducted within the environment. The models have noticed a successful attack phase within the environment here. And so the attribution of the threat uncertainty score is going to be much, much higher. And so what's the first thing that the attacker does? Well, we see them actually successfully sign in, right? We flag the suspicious sign on here. We see them perform their very first suspicious operation within Azure Active Directory. Very simply put, what they're doing is they're creating a new domain within the Azure Active Directory space to set persistence to the domain. They further that persistence by adding principal credentials to email archiving. So very, very early on, before we see our first exfil event, the attacker has access to the entire email archive of the entire Azure Active Directory space. And that's a wealth of data, whether that's sensitive data or not, that's a wealth of data for an attacker to have. Next, the attacker does something that I think, even in today's age, whether we're thinking of it from a zero trust perspective or a traditional industry perspective, is compromise legitimate tooling that wasn't being monitored well enough, right? And so when we look at the Office 365 space, we can compare it to some of the legitimate tooling that exists on a Windows 10 box. If you were to log into a Windows 10 box in any federal environment, I hope, and you tried to open PowerShell, you would receive messages saying that it's incredibly locked down. There's local policy, group policy, enforcement by EDR saying that these executables you can't run as a user. Unfortunately, there is some tooling within the Office 365 space that's just as legitimate and useful to an administrator, but just as powerful to an attacker, right? And so the attack vectors that were presented by Office 365 were not being monitored well enough at this time. And so the first thing that we see the attacker take advantage of is very simple exchange transport rules. What he's doing is he's sending a blind copy of every single email that comes in to the Office 365 space out to his attacker email. And very easily he's achieved exfiltration at this step here. The next thing that he does is he uses EDiscovery to surface all of the data within the Office 365 suite that relates to source code or patent. And we can fantasize about what those keywords would be in a true federal environment. So now the attacker has very easily surfaced this massive wealth of data. He then just as easily uses Power Automate to set flow creation, flow connectors out to Dropbox, SharePoint, and some other API locations to start exfiltrating all of that data within the environment. And so it's important to, from a machine learning model perspective, if we're going to talk about relieving the analyst of investigation and detection, it's very important for us to be able to show an analyst this and say, not only can we surface the behavior for you with a high level of accuracy and reduce the noise in your environment, but we can also track that attack phase of how it pivots from an on-prem compromised host all the way over to an account that oversees and manages a SaaS application as well. And so this is fantastic. We're focusing on doing the one thing that we do well, which is threat detection with artificial intelligence. But in my opinion, as an engineer, that's not enough. And so what more can we do, right? What more can we integrate with to actually take response mechanisms in the aim of zero trust or automation to actually respond to these type of events? What would it look like if an analyst were to create a very simple playbook in Splunk Phantom to actually address this behavior from a host perspective as it was happening? And so first, I think what they would do is they would create a JIRA ticket. They would say, before we take any action, I want to gather all of the forensic details within the environment and relate it to that detection. I want to save that because I'm about to take automated action, but I want to make sure I protect and preserve the forensic details of the actual detection itself. So what we're going to do is we're going to make an API called a Vectra. We're going to gather the C2 detection. We're going to add that C2 detection information into the JIRA ticket, and we're going to extract the C2 IP address within that C2 detection, and we're going to pass that through a reputation service provider. In this case, we're passing it through Splunk TrueStar to say, is this a net new zeroday that we've just discovered, or is this a known bad IP address? Regardless of the result, I want to add that to the JIRA ticket itself. The next thing we're doing is actually taking the enforcement on the endpoint, right? The analysts have said, the first thing I want to do is quarantine the host completely. I'm going to use CrowdStrike to do this. And whatever the result of that quarantine, I want you to update the JIRA ticket with that result. The next thing I want you to do is I want you to block the IP of the C2 node at the perimeter. I don't want this C2 node communicating with any other hosts within my environment, and I sure don't want any more automated instruction sets for self-replication coming to my environment from this IP either. So we're going to block this IP at the perimeter using Palo Alto and add the result of that effective firewall rule to the Jira ticket as well. And so theoretical playbooks are fantastic to talk about, but what does it look like in action? If we go down to the playbook here and actually run this against the host, we get a glimpse of how quickly actions are taking place. And this is very synonymous with how we would perceive actions being taken in a zero trust environment. Very quick, very effective, right? And so for change management purposes, our organization may say, we want to prompt you that you actually want to take action on the endpoint. This is not required, but I think it's really good to showcase that you do have the ability to circumvent some of those fears as it relates to automation. And so immediately you can see these things start kicking off here and how quickly they're almost done. And within seconds, what we find is that there's no data found within TrueStar, meaning that this is a net new zero-day IP address here. The next thing that we see is that the Jira ticket has been created here. The blocking of the IP in the perimeter is being conducted right now as we speak. And so we can verify some of this if we log into our actual CrowdStrike instance here. And also log into Jira to see the associated ticket. And so what we can see here is the ticket. The first thing that we wanted to do was preserve the forensic details, right? This is command and control detection. This is the destination. Here's the source. The state is active. The threat, the triage rules, etc. All of these things are important for us from a forensic perspective for the future, right? Again, the TrueStar report says there's no correlated reports available, which means that the IP we're passing to TrueStar is a net new zero-day, right? And lastly, the quarantine of the actual host was successful, meaning that we quarantined the host successfully. And we can verify that if we go to our host management page within CrowdStrike. We should be able to see very quickly that our host here is contained, right? We have a successful containment on this host. And so again, the reason I show you this is to prove to you that you can rely, or if you can rely on the efficacy of the detection, right? If you can rely on the accuracy that you're actually surfacing malicious behavior, then your response mechanisms can become that more in-depth and that much more encompassing from an analyst perspective and much more effective. And so what I want to do now, very lastly, is pivot to the actual ATARC lab that we have stood up within the ATARC lab environment. And so I want to address a specific scenario, scenario 5, in which where we see an agency has allowed another agency to gain access to fingerprint data within the environment, right? A lot of these zero trust scenarios revolve around legitimate activity being taken, right? And a lot of these scenarios don't point to anything specifically malicious, but how would your tool address this? And how would your tool handle this? And so what we thought we would do is replay this specific scenario, create an actual attack script to go through a very similar set of instructions, but in the vein of what if the agency that was given access to the fingerprint data was compromised by a malicious actor, right? And so one thing that we surface in Vectra is what we call campaigns. And this is the ability for our machine learning models to correlate data and detections across the brain and be able to spit out a campaign for the analyst, right? And so an actual topology of what's going on from an attacker's perspective, right? And why is this valuable? First of all, it very easily clears the mud as far as what's happening in the environment, who is talking to who, right? And what specific techniques are being used to actually compromise the environment. The second thing it does is it provides a solution to the challenge of barrier of entry. A lot of these tools, and especially how complicated zero trust architectures can get, require that you have expert analysts and expert engineers that are able to sift through the data that your tools are reporting. And so it's very important that we provide capabilities within our tool from a machine learning perspective to lower the barrier of entry, to let the junior analysts and mid-level analysts actually provide value to the organization. And so this is exactly what campaigns are used for, which is the ability for an analyst to come in here and immediately see what's going on. This doesn't require them to do investigation. This doesn't require them to draw correlation and context on their own from a single alert. This is already correlated for them. And even more than that, we can come in here and we can see the actual event by event data as far as how did this campaign start? Who was my patient zero? What exactly happened prior to the breach, right? First thing that we see is command and control communication. Then immediately after receiving the automated instruction set or the partially automated instruction set from a C2 node, we see file share enumeration, we see the brute force attempts, we see SMB account scans, we see the actual lateral movement information here, the file share enumeration, right? This attacker trying to actually, enumerate the file share that contains the fingerprint data itself. And then it says, I don't have access to this from my host, so I want to actually do some automated replication, spread some malware and some access potential across the environment, and then start some more command and control and try those lateral movements and enumerations again, right? And so from an event perspective, this is exactly what an analyst wants to see. They want to see a chronological view of what is going on when it relates to cyber threat detection. And furthering that, a junior analyst can easily come in here, click on this specific host and see what has this host done within the environment. Very similar to what we see in the events tab is a new host. We see the command and control activity. We see all of the data transmitted, exactly how our models are seeing it. We see the port scanning. We see the SMB account scanning. We see the automated replication, more brute force attempts, SQL injection activity, until the attacker from the other agency is finally able to enumerate the file share to start actually trying to find the fingerprint data within the environment. And it's very important for models to say, what is legitimate behavior and what is malicious behavior, right? And a lot of these scenarios are something I'd like to talk about. And so if you don't mind, I'm going to go ahead and stop my share here. And I'm going to pivot back over to my PowerPoint slides and kind of talk through a few of the scenarios that you guys have provided to us. Are you guys able to see my PowerPoint slides here?
Yes.
Fantastic. So scenario one, I don't want to read this whole thing to you, but we have an agency employee that's working remotely using his own device. And he must regularly access some kind of public resource for an agency application. This employee travels a lot. His physical location changes frequently within the world. The times he works due to his location also change, right? He also travels to countries that are designated as high threat, right? And this user not just conducts standard user behavior, but he also conducts administrator behavior, right? And so the scenario asks us, what would we do? What would we observe? And how would we handle a scenario in which the user is using administrative privileges to troubleshoot an issue and access another system? Further into the troubleshooting process, which is where the key indicator here is, the user attempts to access a third system, but does not have administrator privileges. From a machine learning perspective, if a machine learning model is learning the behavior of this person's consistent travel, this consistent change in location, consistent change of work schedule, right? Administrative tasks are being conducted at midnight US time, and then 5 p.m. US time, et cetera, right? These are things that a machine learning model would learn as normal, right? And there are some cases in which just because an administrator accesses a system but doesn't have administrator privileges, that's not necessarily a bad thing. That could be anomalous if the administrator has consistently always typed either the correct password or only ever tried to access certain systems. But in the majority of cases, this is one of those fields where it seems very anomalous to us. And so would it actually provide value to the analyst or to the zero trust architecture to limit this person's resources if they had done something legitimate? And so with that, I'd like to say, but what if, as he's traveling to high threat areas, there's specific nation states that if you travel to, you can assume that your personal data and your personal devices have been compromised by stepping off of the airplane. And so what if he's in that location and he's traveled on past that, and then one of those nation state actors chooses to compromise his account? Well, immediately what the models are going to see is that the specific interactions across the network and access with resources are going to be slightly different. And that's not enough to necessarily flag an alert. but they're going to continue learning and noticing that this behavior is not normal within the environment. It's not normal for this user, and it's not normal for the host that he interacts with. And so the second that this host starts trying to access systems that it doesn't have administrator privileges to, the models would say, okay, I've gathered enough context to say that this does not look normal, and it is also indicative of an account compromise within my environment. And that's how we have internally kind of digested scenario one. Is there any questions before I move on? Okay, fantastic. So scenario two, an agency employee working from home from an agency satellite office is using government furnished equipment and using government furnished equipment is accessing internet sites. The sites vary between sites supporting job-related searches or job-related research and interaction with his personal bank accounts, right? And so limited personal use is acceptable per the agency policy. So there's two things to look at here. It is from a personal use perspective of what is acceptable. At this agency is the amount of content that you're allowed to interact with. From a technical perspective, the bytes and bits that you're interacting and sending. For personal use, are these things the limit, or is the limit specific sites, right? Certainly, if each person within the environment is only allowed to access limited amount of sites, right, and that categorizes their personal use, right, then accessing anything outside of that would be deemed as a breach in the policy. And so if the majority of employees are conducting themselves in accordance with the ethical policy that is in place, and suddenly a user is now accessing different internet sites, including his personal bank, that would be a really good indicator that something new is going on in the environment. I can't say for sure that the models would see this as something malicious. This is not something that is indicative of an attacker compromising the environment or something wrong happening. But you can put in place like STIX files and extra threat intelligence on top of our models to say, if these specific sites are being accessed, or from a whitelist perspective, if anything outside of this whitelist is being observed, we can absolutely flag on that behavior. But again, a lot of these scenarios from a machine learning perspective are not identifying anything malicious in them whatsoever. And so with that, we kind of covered scenario one, scenario two, scenario five, and a lot of these follow the same theme of, and I think it's intentional, and we do appreciate that, which is, this behavior is not necessarily malicious, but this behavior is slowly riding to the edge of where zero trust architecture would say, we need to start limiting you resources or limiting the places you're allowed to visit within the environment, et cetera. And so I think with that context, the observability from our machine learning models would absolutely be able to help from that perspective. And so the last thing that I want to do here is pass it off for Q&A, or maybe cover something that you guys have questions on. You have no questions? If so, I will pass it off back to the ATARC team. Thank you guys so much again for allowing us to present our solution in regards to the ATARC lab efforts. And lastly, what I want to do is just for the video purposes, showcase my contact information. If you guys do have any questions or would like to schedule a follow-up, my contact information is here, and I'd be happy to foster a discussion between teams. Thank you so much.
Awesome. Thank you so much, Landon. And thank you guys so much at Vectra for joining us today. I'm going to stop recording.